Algebra 2, Section 5.2, evaluate and graph polynomial functions. We took a look at exponent properties yesterday, and we're going to now develop some more information regarding the use of exponents. And one of those pieces of information has to do with a polynomial. We've worked with quadratics, parabolas, that they were a power of 2, and then we're going to expand that. We're going to look at other types of polynomial functions that are something other than power of 2. Before we get into the other type of functions, let's talk about the fact that polynomial, poly meaning many, monomial is a term, and a term in mathematics can be just a number, it can be a variable, it can be a variable expression. So for example, I could have 5 as a term, I could have x as a term, I could have 5x as a term. When you take monomials and you add or subtract them, so when I add these plus minus signs in between a bunch of monomial terms, I create polynomials. All right, we have color-coded here 3 specific parts of a polynomial that we're going to focus on. The first part, the leading coefficient. Leading coefficient is the very first term of the polynomial. Now, you got to be careful with this one because it is not always the very first number of the polynomial that becomes my lead coefficient. What do I mean by that? You have to make sure that your polynomial is in what we call degree order, and specifically descending degree order. So my power, that is the largest value, would be what starts my polynomial. And it's that coefficient that's in front of that largest power that is my lead coefficient. So you got to make sure, probably one of the very first things we want to do is put our polynomial in descending degree order. Helps me identify my lead coefficient. And then from there, we're good. The last number, the one that doesn't have a variable, or may not even be there at all because it's just 0, is what we call our constant term. And these 3 things we will use. Primarily today we'll focus on lead coefficient and degree of function we will use to help us get an idea of what the shape of the polynomial is. The constant term will come in later when we talk about the rational root theorem and how you can use the lead coefficient and the constant term. So we use these 2, they're factors, as what we call possible rational roots for a polynomial. But that's coming up later on. All right. Here are some common function names. If there is a degree of 0, meaning you don't have a variable, it's just a number. That's called a constant. Degree of 1 we've worked with, those are our linear functions. 2s, we just finished those are our quadratics. 3s are called cubics, 4ths are quartics, and then from there, 5th, 6th, 7th, 8th degree polynomials. All right, the definition of a polynomial. What makes something a polynomial? There are 2 things that we're going to focus on. Determines whether or not you have a polynomial. Two things. We're going to look at the exponents, and we're going to look at the coefficients. So thing number 1, our exponents must be whole numbers. All right, whole numbers, positive counting numbers on our number line. No fractions, no decimals, no variables. The second thing that determines whether or not something is a polynomial is we must have real coefficients. So no imaginaries. If we have those 2, then we have a polynomial. All right, so considering that, and looking at our first example here, number 1, is it a polynomial? If yes, what is the degree, the type, and the leading coefficient? We'll go ahead and just abbreviate leading coefficient with an LC. And degree, we will go ahead and abbreviate with just a degree here. The The type would be the name of the polynomial, cubic, quadratic. All right, looking at these, f of x equals 6x to the 1/2 power minus 5x. The first thing I notice here is, and I always kind of go look at my exponents before I look at anything else. I notice that in this case, I have an exponent of 1/2. And 1/2 is not a whole number. And therefore, this is not a polynomial. All right, there we go with that one. What about b? Taking a look at b, I look at all of my powers. I got a power 5, power 2, power 4. This is a little interesting. But so far, in terms of my exponents, everything is a whole number. It's not in descending order. I would probably want to make sure I put things in descending order just to make sure I'm not losing any of my exponents. But it's not in descending order. But so far, all my exponents are whole numbers. That's okay. That's okay. So my next task is to go look at my coefficients. And I look at my coefficients, those numbers hanging out in front of my variables. Oh, there's nothing there in front of x fourth because that means a 1 is there. So my coefficients are all real. So this is a polynomial. So yes, we have a polynomial. What is the degree of the function? So the degree is the highest power that we see. So I have a 5th degree. And in terms of the type, we said a 5th degree was a quintic. Going back, actually up here we only went to 4th, but a 5 degree is called a quintic, which is 5th degree function. What is the lead coefficient? So type is a quintic, which is 5th degree. The lead coefficient is a -8. All right. C. Again, looking at my powers, whole numbers. Coefficients, real numbers. So yes, this also is a polynomial. It has a degree of 3, which makes it a cubic. And the lead coefficient in front of this one is a 1. And lastly, for D, whole number exponents, real coefficients. So yes, the degree on this is a 4. So that means it's a quartic. And it has a lead coefficient of -3. All right, so there we are. Again, knowing the degree and the lead coefficient type is going to be very useful for us to sketch our graphs. Direct substitution versus synthetic substitution. The direct substitution we're familiar with, but probably not so with synthetic substitution. So let's talk about this. This is what I'm doing to find the values of a function given some x value. So here we have f of x for f of x equals -3x cubed plus x squared minus 12x minus 5, and x is equal to a 2. So we have a 3rd degree function, lead coefficient of -3, constant of -5. What is the value of this thing when we plug an x in for 2? So this is the direct substitution. This is what we're familiar with. We just simply replace every x with a 2. And if we did that, we get -3 times 2 to the 3rd, which is 8, plus 4 minus 24 minus 5. So simplifying all this stuff out, -24 plus 4 is -20. -20 minus 24, -44. -44 minus 5. F of 2 direct substitution solutions. F of 2 equals negative 49. This will then in turn help us later on know that 2, negative 49 is a coordinate on my graph. So function notation gives you a coordinate. That could be useful for me, especially when I'm graphing these things. All right, as always, here's where you can pause and try B on your own and then come back and check the solution. I'm going to keep going though with this. All right, if we were doing direct substitution on this one, again, I'm plugging that 2 in. Just have to remember that you're following the order of operations when you do these problems. Be careful specifically when you have a negative hanging out in front of a variable, and you have to ask yourself, is that negative being raised to the power or not? So here we have 2 times 16 plus 3 times 8 minus a 6 times a 4 plus a 3, 32 plus 24 minus 24 plus 3, so f of 2 here is equal to a 35. Once again, coordinate 235. All right, so that's direct substitution. That's what we're most familiar with. Here comes the new one, synthetic substitution. Now, you're probably going to look at this the first time we do it, and you're going to think, no way, I want to do direct substitution all of the time. Give it a couple tries, because I guarantee you by the time we're talking about doing either long division or synthetic division for polynomials to find zeros or factors, synthetic is going to be a whole lot faster. So you'll get used to it, I guess, probably after 4 or 5 attempts at it, you'll be fine, and then you'll prefer it, and you'll rock and roll with it. But how does it work? So these are the same problem we just had. So we know the answers are supposed to be, for A, it's supposed to be that negative 49 number. How does synthetic substitution work? In synthetic substitution, we want to make sure that we are, first of all, in descending degree order. We want to make sure that we're looking at only the coefficients and constants. And then, we don't have this in this problem, but in the future you might. If you have a missing power, we replace that with a 0. We replace that coefficient with a 0. I'll talk about that when maybe we'll try an example that's different than what we see here, and I'll show you what I mean by that. But for right now, we look at our first one. I have all of my coefficients. Everything's in descending degree order. So the first thing we do is we start with writing our coefficients down. Then I do this kind of like an upside down division box, right? Long L looking thing. Whatever I am directly trying to find the value of f of x from, so I'm trying to find f of x when x equals 2, that number is what we're going to stick out on the left-hand side of this box. All right, so now we're ready to go here. Here's the process. The process goes as follows. When you do synthetic substitution, you drop the first number down. The second thing you will do is you will multiply the value of x that we're using and the dropped number in this case. The solution to that, 2 times negative 3, goes right here. And then you add them up and get a negative 5. And then I repeat that process of multiplying and adding. So again, multiply 2 times negative 22, negative 44 goes here. Add them up, and look at this, a negative 49. So, f of 2 is negative 49, just like we found with the direct substitution, but this time using synthetic. So the solution to synthetic substitution is going to be this last number here. Later on, we're going to learn that that last number we know is a remainder is going to be helpful for us determining whether or not we found a zero, which in turn helps us determine whether or not we can write the factored form of this polynomial. So that's coming. All right, I want you guys to try to be on your own. Again, this is where you would pause. I'm going to go ahead and solve this so you can check back in just a second. Everything is in descending degree order. I start with the coefficients. Put my little box in. This time, though, I'm checking out what happens if x is a negative 2. I drop. I multiply. Get a 2. I add. Get a 5. Multiply. Negative 2 times 5. Get a negative 10. Add. Get a negative 9. Multiply negative 2 times negative 9. Get an 18. I add. Get a 14. Multiply negative 2 times 14. Negative 28. Negative 28 minus 1. Negative 29. So again, it's that process that we were doing, right? We dropped. We multiplied. We added that number here. We got a new number. And then we just kept repeating that process. Multiply, pick that number here, give me the new solution. And we just continued with that process. So the answer here, f of negative 2 is equal to negative 29 for me. Synthetic substitution, very cool. All right. Next thing now has to do with, we've talked about these lead coefficients and the degrees of the function. How do they help me during doing the graphing of polynomial functions? So here, this is an important part also. All of this is important. Has to do with what we call the end behavior. The end behavior. What's going on at the ends of these polynomial functions, graphically? What's going on? So we're going to worry about what's going on in the middle later. For right now, we're just wanting to focus what's happening on the end behavior. All right, there are two things that determine your end behavior. It's determined by the degree of the function and the sign of the leading coefficient. Of the function and the sign of the leading coefficient. All right, just a little refresher. The infinity symbol, sideways looking 8, you can have positive infinity with a plus in front of that, or negative infinity with a negative sign in front of it. All right, we look at the end behavior. We're going to have 4 options here for every polynomial. Every polynomial will have one of these 4 cases. What if the degree of the polynomial is odd? All right, so these two model the odd degrees. Notice where they start and stop, the ends of the graphs. They either start on the lower left and end on the upper right, as is the case for the left-hand option, this one. Or in the other one, they're starting in the upper left and ending on the lower right, so they're switched. What determines the switch is the lead coefficient sign. Is it positive or is it negative? If it's a positive lead coefficient, I end up with this graph that we see here. Now this weird looking notation that's going on in this bubble here. F of x greater than negative infinity as x greater. Okay, these little arrows here means approaches. Approaches. So how we read this is is approaching negative infinity as x is approaching negative infinity. What? All right, let's think about this. If y is approaching negative infinity, that means it's getting smaller. That's happening as x's are also approaching a negative infinity, which means they are in turn getting smaller as well. So basically what this says is as I move to the left-hand side of my graph and keep going, as my x's keep getting smaller, my y's are also getting smaller. And then if I look on the right-hand side over here, I see something different happening. This says my f of x is approaching positive infinity as x is approaching positive infinity. So now what happens is x's are getting bigger and so are y's. And so that's what this in behavior does. It describes what is y doing relative to the x's. So spend some time, put this on flashcards, get this locked into the brain. This is going to be so helpful for us later on, especially when we start talking about rational root theorem. Well, it's going to be helpful for us in our next example, but in the future for sure. All right, those are the odd functions. They start and end in different places. The even functions start and end in the same place. So they either end and stop and start at the tops, like upper, or in the bottoms, lower. Right now, again, you're looking at evens with positive coefficients, start and end up. Evens with negative coefficients, start and end down. Notation, what's going on? Y gets big as x gets smaller. Y gets big as x gets big. On the other side, y is getting smaller as x is getting smaller. And over here, y is getting smaller as x is getting larger. So there we go. The end behavior, very important for us. So let's try doing some graphs. Graphing polynomials. When we graph polynomials, we will plot points, x-intercepts and points in between, and then use the end behavior to determine what's going on with our polynomial. Now we're going to kind of go old school with this for right now. We're going to think about graphing with like a t-table. We'll use a chart, pick our own x values, find our own y values. And later on what we're going to do is we're going to be able to have tools in our belt to be able to take a problem like A, this fourth degree polynomial, and be able to come up with the zeros of the function, another name for x-intercepts. We'll be looking for zeros of the function. That helps us determine what this thing looks like. So those are our points that are going to be in the middle. And then points beyond, those are going to be referring to our end behavior. All right, but for today, we're just going to go and take a look at our t-table study. A couple things to point out might be worth doing. Talk about what degree you see. Make sure the polynomial is in descending order. Look at the lead coefficient. What is it? Well, this one is negative. So my degree is even, fourth degree. My lead coefficient is negative. Now, just from that information, I know that my graph is going to start on the lower left. It's going to end on the lower right. But what goes on in between? Well, that's determined by, for today at least, we're going to pick some numbers here. We're going to pick some x's and some y's. Now, in terms of what values of x and y you use, this is going to be a little bit of a trial and error for you until we get the hang of what these things generally look like. But you're going to have to give yourself more than a couple points, probably like 6 or more points to take a look at what's happening. Because if you don't give yourself enough points, and it's always a good idea to give yourself positives and negatives, you might only see what's going on in half of the polynomial. And then you'll plot your points and you'll say, wait a second, the points I've plotted don't show me the end behavior I'm supposed to see. So here we're going to try -3, -2, -1, 0, 1, 2, 3. I'm going to add a fourth one. Now I've already put these together so I know what the values are. You would obviously spend some time with this. You got to be careful when you're plugging these values in, because here's what we're plugging them into. We're finding, I'll just do the first one with -3. We're finding right now f of -3. And here's where you can use, this is the beauty of synthetic substitution. You can use synthetic substitution to come up with these values. And I'm going to show you real quick how that works. So we've got a -1, and then a 4, and then a -1 for our second degree. Now here, the x to the first degree is missing. So we replace those missing ones with a 0. And I'm going to put a 6. My graph over here. So there it is. We replaced the missing x term with a 0 in my synthetic substitution. Now I'm going to do a little modified synthetic substitution. I'm not going to show you the second step where we show you the bars. And again, this is just something you're going to get comfortable with. So what I'm doing here is I'm generating the y values for my t-table by using synthetic substitution. The first thing I'm going to test is a -3. And here's how it works. I'm dropping the -1. I'm taking -1, multiplying it by -3, and get a 3. I add that 3 to 4 and get a 7. So what I'm doing right now is I am skipping, in our synthetic division process, I am skipping doing this line, the second line. I'm doing that all just in my head and coming up with these values. You guys are smart enough to do that. So then -3 and 7 is -21. -21 minus 1 is -22. -22 times -3 is 66. And 66 plus a 0 is a 66. And then -3 times 66 is -198. And -198 plus 6 is -192. This is your y value. -192. That's kind of an outrageous number for us to plot, but that's okay. All we know so far is that my graph is starting way down there. Now if I kept going, -2, drop the -1, 2 and 4 is 6. -2 times 6 is -12. -12 minus 1 is -13. -2 and -13 is 26. 26 and 0 is 26. -2 and 26 is -52. -52 plus 6 is -46. There's my y value again. And if I kept doing this, I would get the following values for each of these x's. 0, 6, 8, 18, 24, and then finally -10. And I would plot those points. Well, some of them I'm going to plot. I can't plot -192 because my graph scale isn't the right size. So I'd go ahead and I'm going to, let's start with the ones we know. I know I can do -1, 0. So there's -1, 0. And 0, 6, yeah, I can plot that on here. And then 1, 8, yep, you can put that on here. And then 2, 18. 218. Now I have the benefit of having this cool little tool with the smartboard, but you guys would be doing this by hand. You can check it with a graphic calculator, which is a great idea. And then 4, -10. So look at that. 4, -10. I somehow went from way up there at 324 and came down. All right. That's what my points look like. I actually have the equation under here I'm going to use. Here's my graph. I'll move back up out of the way. All right, there's my graph. Now, that's a good, pretty decent sketch. It didn't exactly find like the local maximum here, but that's okay. We got a pretty decent sketch. What I want to pay attention to, though, is did we obey, according to our end behavior, what our graph should look like? Well, it's an even function, and it's a negative lead coefficient, and look what happened. I started down, and I ended down. And that's kind of what these large values are telling us. It's telling me I'm starting way down on the y-axis, y values. there, I made a quick change from a positive to a negative, which again tells me I'm starting down. So you can use the coordinates to see if it's justifying your solution on the end behavior here. And it did. So we have a fourth degree function facing down. All right, so there I am graphing using my end behavior. Again, you can come and check this one out. Freeze it for right now, or pause, and then come back and look at the solution. Here are the values I used. Again, you're going to get better at choosing these values if you work through these. I use -3, -2, -1, 0, 1, 2, 3, 4 again, and then through synthetic substitution found these values for y. And if we took those and we plot them, there's the graph that we're going to get. So I should have been looking at the degree. It's third. More importantly, it's odd. The lead coefficient is positive. So with a positive lead coefficient of an odd function, I start low on the left and I end high on the right, and that's what's going on with my graph. All those other points I'm getting from just plotting my t-table values. So there it is. There's the process that we know now how to graph polynomials. We will learn another process through synthetic division.